All right. Hello, everybody. Hello, everybody. Hello. Many fewer of you than yesterday. Hello, everyone. I hope that you're all doing okay. Welcome back to Comp 3430 Operating Systems. Today, I want to keep on moving with what we were doing yesterday in class. And that is primarily to write code that uses system calls to create and manage a process. So what I really want to do today is I want to take a look at a new system call that's called exec. It's going to help us start launching other programs after we've caused a new process to be created. I want us to be able to think a little bit about how an operating system manages processes from the context of what we're doing with this new exec system call. So how that's changing the process control block that we're working with. Basically, and in short, it's going to take our process control block's virtual address space and replace it with a different program. So when we load our program up, when we ask our shell to start basic io.c or basic io as this compiled program, ultimately what's happening is a code segment is being loaded into our address space, and we're beginning to execute instructions within that address space. When I call exec, what I'm going to be asking to have done is, please replace the code segment in my address space with this code and start running the instructions that are in there. The other thing that I want to do today is I want to spend a little bit of time taking a look at writing some code where processes communicate through message passing. So specifically via signals and pipes. Signals are where we're going to start. And the surprise here, the surprise maybe a little bit, is that you've actually been using signals for a long time. You just don't really know about it. You've been using signals anytime you try to terminate a program to terminate the program. And we'll take a look at how that works, what the operating system is doing underneath, and then we'll try to spend a little bit of time taking a look at pipes. Heads up for tomorrow, please remember that tomorrow's lecture section is canceled. There is no class time tomorrow. What I'm planning to do is to publish a video describing assignment 2. I'm going to give you a tiny bit of assignment 2 right now, but I'm going to describe assignment 2 in a video that I'll post up on the course webpage for tomorrow in a lot more detail. And I'm going to be at the zoo. I'm going to be at the zoo with a bunch of grade 1 students, and it's going to be really fun. And I'm sorry that you all can't come with me, but I mean, the zoo is a public place. If you want to come to the zoo, you're more than welcome to come. But please don't bother me when I'm on a field trip. So with that, before we start talking about managing processes, I want to take a brief look at assignment 2. Assignment 2 is, I want you to implement a shell. I want you to implement your own shell. And I want you to implement your own shell on top of the exfat code that was written for assignment 1. If you really squint at this, and we have to be squinting really hard here, what we're building in this is kind of like Docker, if you know what Docker is. But we're squinting really hard. This is not at all the same idea ultimately as what Docker is, but we're kind of like building a shell on top of an existing volume, and we're executing things from within the context of that volume. The thing that I want to take a look at today specifically is where you could start working on this today, and that's this built-ins part. So I'm going to scroll way down here past the general submission requirements, past the description of shells in general, and I want to look specifically at built-ins. Built-ins here, these are commands that you're going to be implementing that use nothing more than what you've done in a course like Comp 2160. So this is something that you could start working with right now and today. There are 3 commands that I want you to implement here. Built-in commands are programs or tools or utilities, whatever you want to think about them. They are ultimately just going to be functions in your code. You're not going to be doing any extra process management for these. Built-ins are just utilities that you can use, in our case, to navigate around the folder structure. So the first command that I want you to implement in this shell is cd, and cd is change directory. I want to be able to change directory to a different directory, and then I want to be able to print out pwd, what my current directory is, and I want to be able to list the contents of the current directory that I'm looking at. These are going to be just functions. They're not going to be programs. We're not launching anything here. This is just going to work with the kind of like the state of your program as it is right now. These are all going to use our exfat volume underneath, and they're all going to be using the NQP underscore functions that you wrote for assignment 1. I'm providing you with a pre-compiled version of my code, so you have something to work with if you weren't able to get your code working for assignment 1. I think it would be amazing if you could use your own code for this assignment, like build upon this. I think that's cool, but I don't want that to like get you stuck and you can't proceed immediately into assignment 2. So there's some code that you can use already that will help you with this. I also, for the command ls, I am explicitly giving you permission to just copy and paste code from ls.c or nqpls.c in assignment 1. You are straight up permitted to just copy and reuse that code in your implementation of this. You don't have to re-implement that stuff yourself. What I'm going to do now is just really quickly show you what this looks like. So here is my NQP shell, and I'm going to run this on a root.image here. And what we immediately get is a prompt that's waiting for us to type something in. If I type in ls and I press enter, it's going to print out the contents of the root directory of this volume. There's one directory in here that's called dictionary words. So if I change directory into dictionary words and I type ls, it will print out the contents of that directory. If I type in cd ... and I type ls, it will print out the contents of the root directory. These are the built-ins that I want you to be able to implement, and then pwd will print out what directory am I currently working with right now. Some suggestions for your approach to building this. My way to build the idea of maintaining this working directory is that I built up a stack for this. So as I change into a directory, I'll push a new thing onto the stack, the name of the directory that I'm changing into. And as I change out of the directory, so cd ... I'll pop off the stack. I built up a string stack effectively to do this, and then I wrote a little function that's like join all the elements in this stack using the / prefix to get a nice path to a directory. All of these will implement, you will implement this ls, like I said, using the NQP functions. So this will use NQP open and it will use NQP get dents, and then you can kind of work on that from there. I'm gonna, again, I'll publish a video describing the rest of the stuff, but for today, right now, if you want to get started working on this, you can start working on the built-ins part of this without doing any process management stuff. I'm going to promise to have time for questions about this on Monday's class and again on Wednesday's class. So we'll have an open Q&A session for assignment 2, but I want us to get through the term test before we get to that. And so with that, I would like to switch back and I'd like to start thinking about managing processes here. So yesterday we were working with this new function that's called wait. Wait introduces this new keyword to us that's called blocking. When a process or when our code gets stuck because of some other external event that we're don't have information about, or we're waiting for that event to happen, the word that we're using to describe this idea is that our code is now blocked. It is not able to proceed past this point. The wait family of functions are allowing us to wait for the child processes that we create, and it will block our code at that point. This is a synchronization primitive. So this is a tool that we're going to use to begin to be able to guarantee order of execution of things. When I launch processes with fork and I have these printf statements, I can't guarantee exactly what order they're going to print their output in. But with wait, I can now start to guarantee that the child process will finish before the wait is allowed to unblock and proceed. So statements that are coming after that wait are guaranteed to execute after that event has happened. The other thing that we are going to want to do with processes is I want to be able to start launching a new program, and this is what leads us to the exec family of functions. So I'm going to pop over here to my terminal, and I'm going to get out of NQP shell here, and I'm going to change into my examples directory. And we're working right now in the repository that is process management here. So if you want to follow along with me, please clone this repository or pull the repository, because I pushed some changes to it last night. The program that we're going to change here is the process management.c program, and the specific place that I want to start making changes here is going to be in the child process itself. Generally, the approach with exec is that I'm going to fork a child process, and my child process is going to have the responsibility of starting the new program up. It's going to start the new program. That's the pattern that I'm generally going to use for this. I'm going to open up a new terminal to the side here, and the function that I want to use for this is going to be called exec VP. So I'm going to say man3 exec VP. I'm doing man3 exec VP because this is not technically a system call. When I'm doing man2, I'm asking for the system call manual pages. When I do man3, I'm asking for the library call, the library functions. I might talk about this a little more later, what the difference is between what we've got here and what the actual system that we're working on does when we use something like strace to take a look at the output of this code. But for now, let's just start taking a look at what we've got here. There's a bunch of variations of this. There's a bunch of different variations of the exec family of functions that will all take different arguments. The one that we're going to look at here are exec VP and exec VPE. These are going to take 2 and 3 different sets of arguments. The first argument for both of these is the name of the file that contains the program that you want to start. This can be either a full absolute path, or it can be just one single name if the file's name itself is on this thing that's called the path. So there's an environment variable. There's a variable that's available to shells and to processes that are running that just contains the names of directories that we can look in for the names of files. Exec VP and exec VPE both will take the name of the file that we want to launch. The second argument for both of these is going to be the array of arguments that get passed to the main function of that program. So argv here that we're passing is literally the argv that gets put into the main function parameters of the program that's getting started up. Exec VPE takes a third argument, which is these are all the environment variables that our process has access to. I'm going to leave it at this argument exists. We're going to pass values to it, but we don't actually have to care what those values are. The 2 that we really, really care about are the name of the program that we're going to execute and the arguments that we're going to pass to this thing. So I'm going to start by taking a look at running with exec VPE in this code. I'm going to go back up to my main declaration here and make sure that I've declared it so that it has all 3 of those arguments. And I've got all 3 of them, so argc, argv, and envp. And what I want to do with exec VP is I'm going to say, just before I call getchar here, printf. Press enter to switch programs. I'm going to block on getchar. So we're going to get stuck here waiting for some input on standard inputs. And then what I want to do is I want to replace my process control blocks code section with a different program's code section. And so the way I'm going to do that is I'm going to call exec VPE. The first thing that I'm going to pass to this for now is just cat. Cat is the name of a program that we can run on the command line that will just print out the contents of a file. So from process management directory here, I can say cat process management.c, and it will print the entire contents of that file to standard output. That's the job of cat. It just takes a file name as an argument and prints that whole thing back out to standard output. I want to run the program cat. I'm going to pass it an argv array, and I'm going to pass it an np array. The argv array is null terminated. So this is an array of null terminated strings, but the array itself is null terminated. This is a kind of an unusual case with arrays in C where we don't actually pass the number of arguments in the array. We just put a null in the last position of the array, and that indicates that this array does not have any more elements after that. So I'm going to say this: char star star argv cat argv is equal to malloc, and I'm going to say size of char pointer. So I'm going to make an array of pointers, and I'm going to pass 3 total things to this. So times 3. The first thing that I want to pass into this, cat argv at 0, is always going to be the name of the program. And I'm going to do this. I'm going to say strdup. Strdup is a string function that will do like malloc and copy of the string for me, so I don't have to do that myself. I can just get this done for free. The name of this program is cat. Cat argv at element 1 is going to be the file name I want to pass to the argv of cat. So when cat's main function starts, this is going to be argv at 1, and in cat, there's some code that's going to say open argv at 1, read that file descriptor and print, read and print, read and print, read and print until there's nothing left, and then exit. So what I'm going to pass to this is processmanagement.c. So the name of this file. I want cat to run, and I want cat to print out the contents of this C program. The very last thing that I want to pass, Gesundheit, to this is null. This is a null terminated array. This says there are no more arguments for this program when it gets to its main function to do anything with. argc for this will be 2 when main is running inside of cat. I'm going to change this to be cat argv, and I'm going to just blindly pass envp. Envp, I'm going to come right back to this in a second. I'm going to go back up to the top here to my main functions declaration. Envp is something that was passed to my main function. I'm just going to pass it along to this program's main function. I don't want to modify it. I don't want to do anything with it. I'm just going to pass it along to this function's main program. So cat now is going to start. Its process name is going to be cat. The first argument in its args array is going to be processmanagement.c. And then it will have envp just passed to it. I'm going to write this out. I'm going to zoom out. I'm going to make this. I need to include string for string. And I need to include unistd.h. I have unistd.h already there. Whoops. I'm going to open up the manual page for this again. Right. So I'm going to add this to the top of my program here. I'm going to say number define. I want to step through what I'm doing here for a second. Okay, so some of these functions that are in the standard library are not available on all operating systems. So Mac OS, for example, does not have exec_vpe. It has exec_vp, but it does not have exec_vpe. One of the things that we have to do when we're compiling our code with this is to tell it that we are using an operating system that has support for exec_vpe. And what this tells us is that we have to define this value before anything is included to be able to allow that to happen. This is something that we have to do with what's in our assignment, and I've already done it for you, so you don't have to worry too much about it, but it's something that we have to add to this to be able to do it. So I'm going to quit this, and now I'm going to hope that it works. Awesome. Okay, it works. And what I want to do really quickly here is kind of step through what's happening. I'm going to put a get char here because I want to block before we fork. My child process is going to block before we call exec_vpe. So we're going to get stuck here and we're going to wait. The parent process is going to block waiting for our child process to complete. So on line 48, our child process, it's going to be stuck. We're going to be blocked waiting for some kind of standard input to be able to proceed. My parent process will also be blocked on line 64. It's going to be waiting here for my child process to exit before it proceeds. When I press enter, what's going to happen is we're going to call exec_vpe here, and exec_vpe will never return to our code. It's never going to come back. We are asking the operating system to replace our code section with the code section from some other file. We're going to change the context. We're going to change the program counter to be at the main function in that program. And when we do that, we're never coming back to our own code. We are never coming back to our own code. We've fully replaced our address space. Yeah.
Is it always at the start of that program, or can you go somewhere in the middle of that code?
So that's a good question. Can you go somewhere in the middle, or will it always be at the start? With exec_vpe, we're asking to go to the entry point of that program. This is taking us outside the scope of this course, but when you have an assembly language file, there's going to be an entry point that has a common name that's something like start_start, and that will be a labeled location in code that says this is where you should start running stuff inside of this big blob of assembly language code. And when we call exec, we're going to always go to that entry point of that assembly language program. Yeah.
So the first argument is the file name, right? For
the first argument is the name of the process that we're going to create. So when I do PS,
no, sorry, I meant like for exec_vpe, like
the first parameter here, the first argument, this is the name of the program. Yes,
okay,
yeah.
So it's kind of like a separate entity from like the first argument, right? The first argument.
Yeah. So this one up here.
Yeah.
Yes. So I can put this, I can name this like not cat if I want to. I can name this not cat and it will still work. This is the name that's, I'm really sorry, I'm jumping all over the place here. This is the name that's going to show up when I run PS. So this is the name that the process will have. Yeah. No. This is something that outside the scope of this course, sometimes this is actually used to affect the behavior of the program that's running. So like some programs will be compiled in such a way that it's a bunch of programs all compiled into one file. And the way that you tell it to do different things is by running it with a different name. Yeah. But for us, for now, we're just going to say that they're the same thing. Yeah. So exec_vpe will never return to our code. If it does return to our code, something has gone wrong. So the something that's gone wrong is usually I can't find the name of the file that you're asking me to run. Or you don't have permission to run this file, or this is not a program. I can't actually do anything with this. It's not something that I'm able to run. So exec_vp will never return, but the process will end. This process will end because we're asking for a new program to run, cat. Cat has a loop that's going to open up process management.c, open and then read in a loop and print, and then eventually it will exit. And when it exits, then our parent process will become unblocked from this wait. We're going to print hello from parent. And this time when we run this code, there should only be one of these statements being printed out at the end. There will only be one because the child process never returns to our code. We don't have that code in its address space anymore, so it can't come back here and print out this last statement. So I'm going to run this, I'm going to run it. We are currently blocked just before the fork. So we're way up here now. I'm going to hit enter. Our child process is blocked right here, and our parent process is blocked right here. So we've got these two processes that are in a blocked state. I'm going to press enter, and what I'm expecting to happen here is that the contents of the C file are going to be printed to standard output. And then both processes are going to end. So what happens here is we've done exec VPE. We've asked for cat to take over. The first argument in cat is the name of the file, so processmanagement.c. We're never getting to this point in our own code because at this point we're asking for the memory in our process control block to change to be that of cat. Eventually, cat does end when it prints out the very last line of my C program here, and our main function takes over, our main parent process takes over again. It's able to proceed because it's no longer blocked on wait. My child process has ended. It didn't end in my code, but it ended. I printed out hello from parent, which is what we're seeing here. And then finally, the parent process is the only one left that's actually running code in this program. So it's the only one that's going to print out this very last statement here. So what we've got ultimately is, the pattern is, I'm going to start a child process, and my child process is going to be the one that causes this new program to run. My parent process will wait for that process or do other stuff as necessary until that process has finally ended. Yes. This is one case where you actually can't free. Yes, you cannot free that malloc. You can't free that malloc because even if you try to free cat argv, this cannot run. It's never going to get to that point. It will never ever get to that point. However, you can assume at this point that the operating system has replaced the address space for the new process that's being created. Any other questions? We're okay with this so far? Okay, awesome. All right. So we've got these two processes now. We've got the ability to start a new program from one of the two processes that we've got running. And once we've started that new process, we're never going to come back to the code that we have in our own main process itself. This is really good, but the problem with it is that once we've forked, outside of the parent waiting for the child to end, there is no communication between these two processes anymore. If I try to change variables in my parent process or I try to change variables in my child process, it doesn't affect the other process. They're duplicates of each other. When I call fork, I'm asking for my process control block and my virtual address space, so the memory that's been allocated for me for my code and my heap and my stack to be duplicated. When I make changes to variables in one process, it's a copy that's being changed. If I've got another one in my parent process and I make changes to it, they are completely separate places in actual memory. They're different from each other, so I'm not able to do that. But the idea of using fork is ultimately that I want to do work, or I want to share data, or I want to communicate between these processes so that they can accomplish something meaningful across different processes as opposed to being stuck within the same process itself. So I still need to be able to communicate between these different processes. The first way that we're going to do this is to use this idea that is called signaling. Signaling is a pretty basic mechanism for doing inter-process communication, for sending information between processes that have launched. They're limited ultimately to something has happened, period, full stop. That's all I can tell you. Something has happened. We're going to agree upon what it means for different things to happen before we get to this point, but ultimately it's just something has happened. That's primitive and it's limited, but it's still useful. It's useful for things like it's okay to access a shared resource right now. If I have two processes that are working on the same file, and we talked a little bit about this last class with like, if you've got multiple processes that are trying to write to the same file, this is a shared resource. And so we can use signals to send messages back and forth between processes to say, okay, it's your turn to write a complete data structure to this file right now. When you're done, you tell me so that I can write my complete data structure to this file right now. So we can send signals between these different processes to say it's okay to access this shared resource right now. Another is, I want everyone to queue up and get stuck. I want everyone in this process group, so I'm going to launch a bunch of processes, and I want them all to block. And I want them all to wait until an event happens for them to start. There's data available now, so everybody wake up and start trying to do something with this thing. Everybody start now. The last one, and this is not comprehensive, but the last one that I've got here is, I'm going to open a file and write it, and I want you to know that you can open it and read it now. I want to send you more complex information than just a basic, hey, this event has happened. I want you to be able to say, there's something that you can look at right now, so open this file and start working with it. We're going to be using an API to do this, and the API that we're using is this consists of two different functions. One of them is called signal, and the other one is called sig action. We're going to focus mostly on using the signal function as opposed to using sig action. Straight up, signal is the old way to do it, and this is like 1970s old, but it's the old way to do it, and sig action is the new 1990s way to do it, but we're going to stick with the really old one because it's just the simpler way to accomplish the task that we want to accomplish. We can get a little bit more information from sig action, but we don't really care about it right now. The first thing that we need to do is we got to register a signal handler. And the way that we're going to register a signal handler is using the signal function. I'm going to pop open my terminal here. I'm going to open up a manual page for signal. The manual page for signal is, I want to register a signal handler. The first argument here is the signal number. This is the specific signal that I want to listen for, that I want to wait for, that I want to be able to be notified of. All the signals that we're going to be able to do something with are numeric, but they're all constants that we're going to be able to work with. The other thing that we want to tell our signal handler registration is, when my process receives this signal, this is the action that I want you to do. This is what I want you to call in my code segment. Sig handler T is a function pointer, and this evokes like terrifying memories of comp 2160 signal function pointers. If you did function pointers in 2160, did you? Many of you did. Did everyone do function pointers in 2160? I don't think we did. You weren't in my 2160 class, were you? I'm pointing at you as if to say, yeah. You were. No, you were. Who was in my 2160 class? You were. Did we do function pointers? We did. Okay. All right. Okay. So one person in this room for sure knows about function pointers, and it might evoke terrifying memories in them. It's straightforward. It's actually really, really straightforward here. We don't have to care too much about function pointers. We're just going to pass the name of a function to this thing. The function that we're going to pass has to match a signature. And the signature is, it has to have a void return type, and it has to take an integer. That's the function signature that we're going to have for this. So we've got to register our signal handler. And what this is I want to do this when my process receives this event. I want to do this function when I receive this event. Then I'm just going to go and do everything else that I need to do. I'm going to spin around in a loop. I'm going to read a file. I'm going to do the hard work calculating billions of digits of pi. I'm just going to do stuff. I'm going to do something else that my program is supposed to do. Eventually, other processes are going to start sending us signals. And the way that they're going to send us signals is to use either a function or a program that is called kill. This is a terrible name. This is a really, really terrible name for sending signals because, as I talked about when we introduced the idea of processes, we're going to be talking about parents killing their children or children killing their parents, but we're just sending signals. We are sending signals. Sometimes that does actually mean killing the process, terminating it, but most of the time it's just send a signal to this process. The goals that I have for what we're going to do right now is I want to send some signals with the kill command, and I want to send some signals with the kill system call. I want to see what happens when signals are actually received by a process, and I want to figure out which signals that we can't handle. There are some signals that we're not going to be allowed to handle, and to be able to explain a little bit why we can't handle or do something with those signals. If you want to follow along, and I encourage you to follow along, we're working with a different Git repository here. I'm going to do this on Aviary, and I'm going to suggest that you also do it on Aviary if you're going to follow along with me. If you are following along with me, I'm going to be using something called a terminal multiplexer. If you haven't used a terminal multiplexer before, the idea is that I'm just going to connect to Aviary once and be able to launch multiple shells within the same window. If you don't want to use a terminal multiplexer, that's okay. But what I do have to say is if you are connecting to Aviary in two different terminal windows, you have to connect to the same bird in both of them. So connect to Aviary once, look at the name of the bird that you're connected to, and then connect directly to that bird in the second one. So you have the same machine open, the same physical machine open in these two different terminals. So I'm going to SSH here to Aviary. And I'm going to use a terminal multiplexer that's called tmux. When you see my shell open, I often have this open already. And when I'm doing window splits and stuff, this is what I'm doing. Yeah.
Two processes can't communicate, right? So if they can both access the same file, isn't that technically compatible?
That's a fair question, and that's a fair point. So the question is, if two different processes can access the same file, can they not communicate through that? Yes, they can. But the key to what we're going to do right now is they have to be able to tell each other when it's okay to open and read and write to that file. Because if your process is just kind of randomly opening a file and trying to read it, or randomly opening it and trying to write it, you don't have any guarantee that says there's actually data there, or it's okay for me to make changes to the file that somebody else is reading right now. So our approach with this is going to be to use signals to have some kind of synchronization that says, yes, you can open this file right now and read it because I've just written data to it. Or it's okay for you to write to it now because I'm finished reading this file. But that is another way for processes to communicate with each other, yes. Yeah, okay. So I'm going to clone this repository. So git clone https://code.cs.umanitoba.ca/comp3430-summer2025 /interprocess I'm going to change into this directory, and I'm going to open up a new terminal to the side here, and I'm going to change into that same directory. In this directory, I've got 3 C files. I've got a make file and a readme. The make file is a make file. The readme, I'm going to tell you what these files are right now, but it describes what the files are and how to work with them. The one that we're going to work with right now is called signal.c. I'm going to pop open signal.c, and I just want to take a quick look at what's in it. There's not much here. It doesn't do any process stuff at all right now. All this does is print out a fancy spinner. That's all it does right now. And it does this forever. It will just spin around forever, printing out this thing, erasing it, printing over it, erasing it, printing over it, erasing it, printing over it, and it looks like this nice little animated spinner. I'm quite proud of this, so I hope that you all appreciate that. I'm going to make this, and I'm going to run signal. If you are following along with me, the very first signal that we're going to send to this process, and I'd like to do this all together, you're going to need 2 fingers. You're going to have to hover one of them over the control key and press it, and then hover one of them over the C key and press it. And we have just sent a signal to this process. The signal that we sent to this process is the interrupt signal. I want you to stop what you're doing right now. Signals have a default action. The default action for the interrupt signal is stop, exit, stop doing what you're doing and terminate. I want to register a signal handler in this code because I want to do something different when I receive the interrupt signal. To do that, we're going to use the signal system call. So I'm opening up the man page again for signal here, man2 signal. I need to include signal.h. So I'm going to go up to the top of my code here, and I'm going to add include signal.h here. I need to write a signal handler. So I'm going to say void handle signal, and it must take an integer. The number that is being passed to this function, it represents the signal that is going to be, that has been sent or that has been received by this process. Within this, I'm going to say printf handling signal %d\n signum. I've declared my signal handler, and now I have to register my signal handler. To register my signal handler, I have to call signal. I have to pass it the signal that I want to handle. I'm going to scroll down here, and I think I'm going to open up a different manual page. I'm going to open up a different manual page. So I'm going to open up man7 signal. Section 7 of the manual pages is high-level descriptions of concepts. And so this is a description of signaling as a concept. But the important part about this high-level description of signaling as a concept is that it has, if we scroll down a little bit further here, a table of the names of the signals that we're going to be able to work with. So the one that I want to work with right now is this one, sigint. The default action for sigint is to terminate. This is what my process will do by default. When my process control block is created, this set of signals that are actionable or the things that we can do, they have these default actions, and the default action for sigint is to terminate. And what I'm going to ask here is, I would like to replace the default behavior for the interrupt signal. So my process control block will have a table of these signal handlers, their function pointers. This is what's going to get invoked when I receive this signal, and I want to replace that action right now. The second argument that I pass to this is going to be the name of the function that I want to invoke. So handle signal. In my other terminal here, I'm going to make this, and I'm going to run signal again. And I want to send another signal to this. And so I am going to hold down the control key, and I'm going to press C. And I'm sending a signal to this process. It's handling the signal. But it ain't exiting. Yeah, yes, yes. The number 2 here is what sigint is. So our signal handlers it's a table, so it's an array in our process control block. And sigint is number 2 in that array. It's an array of function pointers. And by default, at position 2 in that array, it's to exit. And so what's happening here is I'd like to replace number 2 in my array with this function. So replace whatever the terminate was with this function. This function is going to run when I get that signal, and it's going to print out signum2, which happens to be sigint here.
Okay, because you're pressing Control C, right?
Yeah. So when I'm pressing Control C here, I'm sending signal sigint to this. I'm going to open up another terminal here. And what I want to do is I want to send a signal to this process in a different way. I want to use the kill program to send a signal to this. I'm going to say kill. And what I pass to kill is either going to be dash uppercase SIG and then the signal that we want to send, or it might also be just dash int. It depends on the shell that you're using that says which one it is. So you may or may not have this sig prefix. I'm going to add the sig prefix. And the thing that we want to send the signal to, I'm going to have to scroll up here, is the process ID. So this is the process ID that was printed out for this process when it started. And when I send a signal to this process using the kill command, it's doing the same thing, but now it's a completely different program that's sending this message to us. I do actually want to terminate this process. I do actually want it to stop. And so the way that we're going to terminate this process is to use not sigint, but sigkill. Sigkill is going to force a process to quit. I'm going to try and replace the signal handler for sigkill. I'm going to make this. I'm going to run it. I'm going to hit Control C. Still does the same thing. I'm going to send the sig kill signal to this, so 490138. And I'm not allowed to change that signal handler. My OS is going to look at this entry in my signal table and say, no, actually, you can't. And in reality, if we were to take the path through our operating system is going to interfere with that flow. It's going to say, is this sig kill? And if it is sig kill, I'm not even going to send a message to this. I'm just going to cause this process to exit. I'm going to terminate that thing. So what's happening here is, we cannot do this. Can't replace the kill signal handler. We're not allowed to replace the kill signal handler. Our loop here is spinning forever. Our process is going to be in the state of it's ready and it's writing, it's ready and it's writing, it's blocked and it's sleeping. It's ready and it's writing, it's ready and it's writing, it's blocked and it's sleeping. It's ready and it's writing, it's ready and it's writing, it's blocked and it's sleeping. And it just keeps on going into this thing forever, into this loop forever. We've registered the signal handler by calling the signal function. And what we're asking the operating system to do when we send signals to this by pressing Control C on our keyboard or by running the kill program is we're saying, operating system, please send a signal to this process. Our operating system is going to ask the question, is this process actually a process? Is there anything for me to send this to? If the answer to that is yes, it's then going to ask, are you allowed to send a signal to that process? So I'm going to run PSA here. This looks like a distributed computing assignment that's happening right now. And I'm going to do this. 221. Good, good, good. I'm not allowed to kill somebody else's processes. I'm not allowed to send signals to somebody else's processes. We're asking the operating system, this is a system call that we're making with kill. We're asking the operating system, please send this message to this process. The operating system is going to say, do you have permission to send it to this process? And if you're not, it will refuse. It's not going to allow you to do it. If you are allowed to do it, we're able to find the process and you're allowed to send a signal to it, then what's going to start happening is our operating system is going to start manipulating the state of this process. It's going to manipulate the state of this process by whatever it's doing right now, it is going to add a new stack frame. The new stack frame that it's going to add is our signal handler itself. We're going to add an entirely new stack frame to whatever it's doing, wherever it's doing it. We're going to add this new stack frame. We're going to set the stack pointer to that stack frame, and we're going to set our program counter to start executing instructions inside that function that's on the stack. We're going to do everything that's in our signal handler, and then we will eventually leave the signal handler. We'll pop that frame off of the stack. And then we'll just go back to wherever we happened to be before that was pushed onto our stack. So if I was in the middle of erasing with \r here, carriage return, and keep talking about these typewriters, carriage return is where it takes that print head and it moves it all the way to the left side of the page. Carriage return here is take the cursor and move it to the left side of the screen so that you just overwrite what was there before. If it's just done this carriage return, then we're going to add a stack frame right after that. We're not going to get this thing printed out. If it's just printed that out, we're going to stop it before it's allowing to go to sleep. If it's in the middle of sleeping, we might even wake it up and run the signal handler and then go back to sleep after we're done because we were in the middle of sleeping. So signal handling is, I'm going to add the stack frame, I'm going to do the stack frame, I'm going to return from the stack frame and just go back to wherever it was that I was before. The last thing that I want to do with this is I want to add to this and I want to be able to send messages between two processes that I've started up. So the way that I'm going to do that is I'm going to use fork to cause a new process to start. I'm going to declare a new process ID type, so PID-T, child process. I'm going to say child PID is equal to fork. We're going to follow that same pattern that we had before. We're going to have a conditional statement that asks the question, what is the value that was returned to us here? If child PID is equal to 0, we're running instructions in the child process. And if we're not running instructions in the child process, then I'm just going to let this proceed into the parent. So I'm not going to have the else block for this. I'm just going to have the if part to say if I'm in the child process. In the child process, what I'm going to do is I want to send a message to the parent process when I've finished doing a little bit of work. I'm going to say printf in the child process about to do hard work. And then I'm going to go to sleep for 5 seconds. After I've done the hard work, send a message to my parent to say that the hard work is done. To do this, we're going to use the kill system call. the kill system call takes two arguments. One is the process that I want to send the message to, and the second is the signal that I want to send to that process. In the child process, I need to know what my parent's process ID is. And I can accomplish that in two ways. One is I called my get PID before I called fork. And so the value that's in my PID is the parent's process ID by the time I get into the conditional statement here. The other way that I can get the parent's process ID is to call get ppid. So I'm going to say PID-T parent ID is equal to get ppid. Get parent's process ID can also use my PID. It called get PID before fork. I'm going to say kill parent ID. And I want to send it a signal, and we're not going to send sig int or sig kill here. We're going to send a different signal. I'm going to say sig user1. So I own both ends of this code. I own the child process and I own the parent process. So I'm going to say that the child process is going to send sig user1 when it's finished, and the parent process will wait. It will register a signal handler for sig user1, and it will know what it means when sig user1 has been sent to it. I'm going to send this signal to my parent, and then I'm going to go back to sleep for a little bit. I'll go to sleep for 5 more seconds. And then I'm going to exit. So my child process here is going to block itself. On line 42, we're getting blocked for 5 seconds. Sleep is a function that I'm using to just say I want you to not do anything for about 5 seconds. I'm going to ask for my parent's process ID. I'm going to send a signal to my parent to say that I'm awake now. I've finished doing what it was that you asked me to do, or I finished doing the hard work that I'm supposed to do. I'm going to go to sleep for a little bit longer, and then I'm going to exit. So I'm not going to proceed any further in this code. What I want my parent process to do now is I don't want to sit around spinning forever. Sit around spinning for what feels like forever as you wait for your child process to put its shoes on. So doing hard work of some kind. I don't want to spin around forever. So what I'm going to say here is while not flag, I'm going to declare a new flag variable, and I'm going to declare this as a file scope variable. So outside of my functions, I'm going to go up to the top of my code. I'm going to say int flag is equal to 0. And when I'm handling this signal, I'm going to say flag is equal to 1. So I don't want to proceed past this point until I have received this signal. I want to block until I've received the signal. I'm going to register another signal handler here for that sig user1. I'm going to go back down to the bottom where I've got my loop here. I'm going to say printf, child is finished. Then I'm going to wait for that child to finish. Child has exited. Exiting. So our order of operations here is before we do fork, I'm going to register these signal handlers. I'm doing this before I call fork because I want to be able to guarantee that I've registered a signal handler before my child ever tries to send me the signal. If I register these signal handlers after I call fork, I cannot guarantee that I'm going to be able to register my signal handler before the child it calls kill, before it tries to send me the signal. So I want to guarantee that this is going to happen by calling signal and registering these signal handlers first. Then I'm going to fork. I'm going to duplicate my process control block. And now both of these processes have signal handlers registered for those signals. We've duplicated our process control block, so the changes that we've made to that signal handling table are kept across this fork. The child process will print out a message. It will go to sleep. Then it will send the signal to our parents. It will go back to sleep, and then it will exit. It will leave. Our parent process is sitting around here waiting for that child process to send the signal to it. So we've established this synchronization point. We are blocking. The loop that we have here is now causing us to be in a blocked state. It's not necessarily changing the state in the process control block, but we're not going to be able to proceed past line 73 until that message has been sent to us by the child process. After the child process does send us this message, we're going to print out the child is finished. We will wait for that child to actually exit now. So we'll use that same synchronization primitive that we had before. We're going to block here. Then we're going to exit ourselves after that. So I'm going to write this out. I'm going to make it and cross my fingers. Haven't included wait.h. I think that's what it was. Man to wait, sys wait. So I'll go back up to the top and do that. I'm going to make this again. I'm going to zoom out of this. So I'll quit that and I'm going to run signal. So the parent process right now is spinning in that loop. Our child process has just sent the signal to it. Our child process exited. Our parent process was blocked here on wait, and it finished because the child process itself exited. So now what we've accomplished is we've registered signal handlers. We've set this up so that we can actually do something different if one of these signals is sent to us. We've sent signals to a process using our keyboard, so pressing Control-C to send sig interrupt to this thing, and we're no longer terminating. We've replaced the default action there. We've used a program to send messages, send signals to a process, that kill program. And now we're sending messages between processes using the kill system call. And we're using flags to do things like synchronization and blocking to stop, to do synchronization stuff. I've been shouting at you all a lot. How is this feeling so far? Is it okay? Okay. Does anybody have any questions about this before I proceed into something else? Yeah.
Is there a reason you're sending 3 signals at the top, hint, USR, and kill?
I'm registering the 3 signal handlers here. This was kind of just like, it grew to be bigger and bigger and bigger each time I did it. But generally what I'm going to do is only register the signals that I'm actually interested in handling. So sig kill, I'm going to leave this one here because I want this to be in the repository that you have access to see the comment that says we actually can't register a signal handler for sig kill. We're not permitted to do that by the operating system. For sig int, this was just initially, I want to be able to send signals with Control-C, and sig user 1 is I don't want to send sig int from my child process. I want to use a different signal to be able to do that.
They just correspond to different things that you do with people, right?
They're corresponding to different kinds of signals that our process can receive. So I'm going to open up man7 signal here again, and I'm going to go down to that table. And there are many different signals that can be sent to a process. One that can be sent to us that might be a little surprising to you is that one. And we're going to take a thrilling ride through the kernel in a couple of weeks to find out what's actually happening when the words segmentation fault are printed to our screen. But the hint here right now is that it's a signal that's being sent that's causing our process to exit. But there are many different signals that can be sent to a process. So user 1 and user 2, these are ones that have been set aside for I want to use this for my own specific purpose.
Okay.
And so I want to be able to send that message. Sig interrupt here, this is a well-defined thing. It is interrupt from keyboards. It is Control C. This is the signal that gets sent to a process when we hit Control C on the keyboard. Yeah. Yeah.
Yeah, right. So you repeat, I don't understand the thing you said previously about a new stack being added when the signal will give the state, right?
Yeah, absolutely. So I'm going to go back to my code here, and I'm gonna do this, and I'm gonna regret it immediately. I'm gonna split Vim. So I'm not splitting tmux here, I'm splitting Vim because I want to have the same file open in two different places. On line 69 through 74 here, our parent code is spinning. So we've previously registered these signal handlers up here on line 30, 33, and 35. This says, I want you to run this function. I want you to add a stack frame for this function when the signal is sent to me. But then it just proceeds. It just goes on doing other stuff. The other stuff that it's doing here is write and write and sleep and write and write and sleep. And it's just going to constantly spin on this until something happens that causes it to leave that loop or something else is happening. What happens when we call kill here on line 58 from the child process is that the operating system does a bunch of checks. Does this process ID exist? Is this process allowed to send signals to that process? And if it is, it's going to add a new stack frame in the process that's receiving the signal, interrupting whatever it is doing right now. So whatever it was doing, whatever our parent process was doing right now was this, spinning around in this loop endlessly until this flag is set. When the operating system interrupts, it's going to add a stack frame to the stack for that process. It's going to change the context, so it will change the stack pointer and it will change the program counter to start running this printf. And then it will switch to that process. And that process will start running this function instead of wherever it was before. Once it leaves this function, so when it returns from this function, it will pop off that stack frame, and popping off that stack frame will result in it just going back to whatever statement or instruction it happened to be on before. Yeah. Every time a function runs, but in this case, every time a signal is received by the process, yes. It's yeah, jump starting a new function. That's a good way to think of it. Yeah, yeah. Any other questions? Yeah.
So the big kill, that's the one that we can't read it or write. Is there a way that we kind of schedule, or will the OS always do it right on a kernel level, or get that way?
We would have to modify the Linux kernel source code to ignore sigkill effectively. Once we call kill here, and in the kernel, I see that this is sigkill. When I get to the point of, in the Linux kernel, I want to add a new stack frame for that process that's on the receiving end, I just don't add a stack frame. I just terminate the process. I just tell it, you are ending now. You are ending now and you terminate. So that signal never actually reaches the process itself. The process is killed by the operating system before it would get to that process. Yeah. Sigkill is so that, well, basically, so Rob can't just install a Bitcoin miner on your laptop and you can't stop it. Yeah, if Rob starts his Bitcoin miner on your laptop, and I'm saying this lovingly, by the way, with Rob's distributed hash table assignment, if you have had to endure that, yes, Rob can't just start a process. He can't get access to your system and then start a process, and then you can't kill it. We don't want that to happen. We don't want your fans to just be spinning while Rob's mining Bitcoin on your laptop. You're the administrator of your laptop. You should have permission to kill his processes. And the way that we can accomplish that is you get permission because you are the root or administrative user of that system, and I want to be able to tell that process to stop. I don't want it to just keep going. If it was able to handle the kill signal and not exit, if you even sent it the kill signal, it would just keep mining Bitcoin. We really don't want that to happen. Yeah. Yeah. Okay. Yes. It turned red, so that means that it's actually something that we can do. Then what I need to do, I can even do this before the fork. How am I going to do this? I'm going to say char something is equal to null. Printf, the value of something is %s. Dereference something. This should segfault. I'm also going to comment out this because I do actually want to be able to kill this code. I'm going to zoom out. I'm going to make C. Okay, it should be a C instead of an S. Okay. All right. Okay. So think about this now. Just take a moment to think. Predict the output. I'm not answering any more questions about this right now. We will talk about this later. So this is your preview to virtual memory in 2 weeks. It's just constantly printing this out. I'm pinning a CPU, like I've got 100% CPU usage just printing out handling signal 11 right now, over and over and over again. And I'm going to hit Control C. I don't want to have SIGINT stopping this, so I'm going to hit Control C and stop it. Yeah.
So I tried to shut down some of the Python process before. If you're the system administrator, like the other administrator, could you do that?
Yes. So the question is, I'm going to zoom in here. I'm going to run PSA again. Yes, I'm on Aviary still. And so when I try to do kill -sig kill, I don't know what this is, somebody's SSH session to some other machine. I'm not allowed to do that. If I were the administrative user, so if I did this, sudo says, make yourself the system administrator and then run this command as the system administrator. I'm not going to hit enter on this because this will send an email to our tech staff, and I don't want them to see that I'm trying to do stuff like this in class. If you are running on your own system, so you got a Mac there, you have sudo on your system. When you run sudo, it asks you to type your password in. You type in your password, it elevates you to the administrative user, and then yes, you can send the kill signal to other processes at that point, yes. And I'm going to hit Control C on this because I don't actually want to send that message. All right.
And that kills the parent process or whatever other process, not yours, right?
The kill here would kill whatever process has the ID that I'm passing.
Okay.
Yeah, yeah. All right, so summarizing here, our operating system starts by accepting the request to change the signal handler for the specified signal for the process. When I call signal, when I make a call to signal, I am asking, please operating system, in my process control block, change the function pointer at entry n in this table, and I want this function to be invoked instead when I receive this signal. This is the stack frame that I want you to add. Then I do stuff. I start running the process itself. So our operating system accepts the request, and then it does whatever else it needs to do to get that process to run. We'll talk about scheduling policies soon, but ultimately we're just having other processes on the system behaving as normal. They're running, they're doing their own thing. it will eventually receive the request to send a signal to another process. Either I've hit Control-C on my keyboard, I'm running the kill program, or I'm sending kill with the kill system call itself. So somebody else is asking to send a signal to another process. I've got to find the process ID. So in my list of process control blocks, I'm going to find the process that has that ID. If it exists, I'm going to ask the question, does the user that is owning this process that's sending the signal in the first place even have permission to send it? If it doesn't, reject it. So operation not permitted here, reject it. And if it does have permission, then proceed to sending the signal. Sending the signal is, I'm going to add a stack frame to the stack area for this process itself, and then I'm going to modify the context. So I'm going to modify the context to be pointing at that stack frame with the program counter and the stack pointer, and then I'm going to do the context and mode switch to actually start that process up so that it can begin running instructions in the signal handler itself. This is where we're going to get today. I'm going to summarize this really quickly, but the problem with signals is that we can't actually send anything to another process. I can't send data to another process. The question you were asking, can we use files to do this? Yes, and in fact, the pipes API here allows us to do that with file-like things. We're not going to create files to do this. We're just going to have in-memory structures that are being used to send information back and forth, but we're still going to use the read and write system calls to be able to do that. Like I said, I'm going to post a video for tomorrow's lecture describing assignment 2 to give you a better sense of where you can start with that. But after today's lecture, what you should start to be able to do now is to be able to get to the point of doing launching processes and beginning to start to do the input redirection. But like I said, I'll put a video up to describe some of this stuff for you. At this point, however, you should be able to write code that uses system calls to create and manage processes. You should be able to describe a little bit about how the operating system manages processes in terms of data structures, control of the processor and modes, and you should be able to write some code that processes communicate with each other with signals, sending signals to each other. That's it for today. I hope that you have a good rest of your day, and I will see you all on Friday. Okay, bye everyone.